So today we are very happy to have Greg Bodwin from University of Michigan visiting us. Greg is an assistant professor there. He's been there for a couple of years now. He's been doing amazing work on spanners. So, okay. I want to say extremal graphs also, but okay. And he's around today if you wanted to chat with him. And there's also a student meeting afternoon. Evening. All right, good. So I will not say anything more. Let's check.
Cool, yeah.
The light. So then it will make this light. It will like all. I'll try it once.
This good? Cool. Okay, let's get started. Yeah, thanks for the introduction. Thank you all for having me. Just to echo that, I'm around for a little bit. We'll love to chat with you today. I work on this stuff and also many other areas, so if this is not exactly your cup of tea, feel free to come say hi anyways. So let me give you actually a little bit of background on this talk before I start. This is a survey talk. It includes a ton of papers, some of which I was on, some of which I was not. I've been giving a version of this talk for a few years actually. And in most of the past versions that I've given, I like talked about fault tolerant spanners for a while. And then the conclusion of the talk was I was like, and like we basically understand what's going on now. There's a few open questions here and there that we're supposed to figure out, but like the situation is pretty good. And then within the last year, basically, something happened. And now the conclusion of this talk is going to be I have absolutely no idea what's going on with fault tolerant spanners anymore. So I changed the title to something much more clickbaity from like, we've made progress in fault tolerant spanners to like, we're on this quest to actually just understand the basic definitions and play here. And I'll go through that. This is basically going to be one big long approach to an open question at the end. That's what we're trying to do. So I'll get there eventually. Definitely feel free to jump in if you would like more details on anything. Happy to like kind of, not going to do a lot of proofs here, but if you want to see any more details, everything is pretty great. I can jump to a whiteboard or something like that. Okay, so we'll get started. Thanks for having me. And it looks like my clicker is dead. Just a second. There we go. Okay. So what we are talking about at a super high level here is graph sparsifiers. There are a bunch of different graph sparsifiers that are out there in the world, but the basic template for research on graph sparsifiers, of which I will talk about a couple specific types, is this. So you get some graph G, which we typically imagine to be some enormous graph, kind of like that one on the right, much, much bigger than that, but that's the cartoon here. And your goal is to come up with a much smaller, typically subgraph of G that preserves some sort of important structural properties of the original graph, perhaps up to some approximation. So this one on the right, it is over the same vertex set. It has many fewer edges. And it turns out that if you look at any two nodes on the left, the shortest path distance between those nodes is within a factor of 3 of the shortest path distance between that same pair of nodes on the right. So therefore, the idea is like, if you had to solve some distance-based graph algorithm over the one on the left, but you're willing to tolerate a little bit of approximation, you might as well use the one on the right. It's going to be a lot faster in exchange for that approximation. So that's what we're doing. The other like specific thing about this talk that is not true of all talks is that the focus is going to be entirely on existential results. By which I mean, you could ask the question like, given a large input graph, find me a fast algorithm that computes a good sparsifier. But that's not really what we're doing here. We're just trying to say like, what sorts of sparsifiers always exist no matter what represents like a structural fact about the graph. Let me give you just what I think is the absolute most basic example of a graph sparsifier, like what we're talking about. So this is a connectivity preserver. Connectivity preserver of some graph G is just an edge subgraph. Edge subgraph means you have to keep all the vertices, but you can remove edges. That has the same connected components. For example, this. We've come up with a connectivity preserver H. It removes one edge from the original graph. So, you know, that's a win, although we'll hope to remove more in general. And it has the same connected components. To quickly, you know, hopefully you don't need to motivate this too much, but just to kind of set the pattern for what we'll be doing for the rest of the talk. The way to check that this is a good definition, something that is worth studying in this area, is, first of all, it should be the case that every graph is trivially a sparsifier of itself. Of course, it doesn't actually sparsify itself, but it would better satisfy this property we're talking about. Here, that is clearly true. Every graph has the same connected components as itself. The other thing that we should check, though, is it's not enough just for the definition to make sense. We also want to be speaking about objects where we can prove non-trivial theorems. It's not interesting to say that like every graph has a sparsifier on the most n-squared edges. We would like rather a theorem like this that says every n-node graph has a connectivity preserver on some interesting number of edges, order n. For example, a spanning forest will do, but of course that's not the only type of connectivity preserver out there. I'm a little bit worried about things getting cut off at the bottom. I might have to adjust things if I get text that's too low on the slide. We'll see.
What is another way of doing that without the spanning forest?
Just if I were to like take a spanning forest plus a few edges or something like that, there's some like sublinear algorithms that will produce that. It would still count as having order at edges and to preserve connectivity.
Are you going to give me an example where you might want a sparsifier that is not a subgraph?
I will not be talking about that in this talk, but there absolutely are examples of that in a while.
It's a good idea.
Yeah, probably the most famous example is spectral sparsifiers. These are not subgraphs of the original, rather they're just some different graph with differently weighted edges that happens to have something in common with the original. Okay, so this is one example. The other objects that I'm going to talk about a lot here, it's just sort of a slight extension of connectivity preservers. These are spanners. So a spanner is where instead of only needing to preserve connectivity between any two nodes, you more strongly need to give me a distance approximation between any two nodes. For example, this same graph that we did before is in fact a three-spanner of the graph on the left. That's because if you look at any two nodes, for example, these two, the distance here is 1. The corresponding distance here is 3. That's within a factor of 3, so it counts. You can perform that check over every node pair, and it'll work out how you want. Okay, so K-spanners, these are the other things we're going to be talking about. Just to quickly run through these motions, is this a good definition? First of all, every graph should trivially be a K-spanner of itself. This is indeed the case, assume K is at least 1, as we will. The other thing that we should check is, do non-trivially sparse spanners always exist? This is not quite so obvious and well known in the same way that it was for connectivity preservers, but it does wind up being true. There's a classic theorem from 1993. I'll say more about the proof significantly later in the talk. But it just says every n-node graph, if you give me any integer k, you can always come up with a 2k minus 1 spanner that has this non-trivial sparsity bound at the end of the 1 plus 1 over k. This is conjectured to be tight, but it's an open question in some sense. Okay. So these are the main two objects that we're speaking of here. And among other things, these objects, specifically spanners, were invented for the sake of applications in networking and also distributed computing. And the basic idea is this: you have some sort of large network of communication links that you're trying to use. And maybe these are expensive links to maintain. So what you're going to do instead is only maintain some kind of spanner of that original graph. This is a much cheaper thing to maintain. It's a 3-spanner, and therefore you can still kind of pass messages from source to destination with like a 3x the latency or something like that, but that's not so bad. 3 milliseconds instead of 1 millisecond, and it's a much cheaper thing to maintain. You can totally imagine situations where this is a good idea. So the theorists kind of came along and they were like, okay, look, like use these instead of whatever you were thinking of using before. It turns out that this completely does not work in practice. The thing that stops this from working in practice is that nodes and edges can fail very commonly in these networks. They'll go down for a bit, they need to be repaired. And the rest of the system is supposed to keep working. So for example, if that thing right there fails, that node breaks, then all of a sudden the subgraph that you maintained is disconnected. And you really regret having listened to the theorist who told you to only keep that subgraph. The original thing is fine. If you had kept all the links, you'd be fine. Everything would still be connected. But now it's not. So the barrier to using this stuff in practice, or at least one of the main ones, is that these objects are not by nature fault tolerant. So in other words, connectivity preservers and spanners, these definitions are not strong enough. So therefore, we shouldn't just give up and go home. We should, oh no, I have a crash here. There we go. Yeah, so we need some sort of like additional spiciness on top of this definition that's going to equip it all with fault tolerance. So that's what we're trying to do. This is clearly a good idea conceptually to add some fault tolerance to these definitions, but it's easier said than done. How do we actually go about formalizing this? And that's going to be the focus of this talk. Okay, so here's a pretty good first attempt at formalizing fault tolerant. I'm going to call it absolute fault tolerance. So here's the definition that I'm going to put down first. We'll say that you have an F, absolute edge fault tolerance connectivity preserver. You can also define the analogous thing for vertex faults or for spanners, but I'm just going to start here. If basically for any set of at most F failing edges, the faulted graph that you kept still has the same connected components as the original graph. So in other words, like this promise about having the same connected components, we're making it even stronger. We're saying like, even if this particular edge were to fail, or really any edge, it remains the case that the connected components are the same, just one big connected component in this particular case. Okay, so one of the reasons to start with this is, I think, historically the first definition of fault tolerance that was used, specifically because there's an enormous approximation algorithms literature on something called survivable network design, which is basically the algorithmic problem of finding the smallest possible subgraph with this property. So what do you think? Is this a good definition to use?
First question in the opposite direction right here.
Yeah, what is that?
In the sense that if there's only one edge between two parts of the graph, and you get rid of that, you're in trouble.
Yes, you're exactly right.
Clearly, you got to throw in something that's not part of the original graph. So that was what I answered before.
Yeah, so you're exactly right. So you're hitting on the point that I wanted to make here, which is that even though these have the same connecting components in this particular example, this is a bad definition for exactly the reason that you just said, which is it fails this first test that every graph is supposed to be a sparsifier of itself. Specifically, here's the simplest example. I just drew a one-edge graph, but of course you could just imagine this as being a cut edge in a much larger graph. It is not the case that that graph is a one absolute fault-tolerant connectivity preserver of itself. It is possible for a fault to just fundamentally change the connected component structure of that graph. So, okay, what are we going to do about this? One way that we could try to finish it is, like you were saying, maybe like allow ourselves to add some new edges that weren't in the original graph or something. But actually, the more common way around this is like this. So instead of using absolute fault tolerance, we're going to use this notion of relative fault tolerance. And the only difference in this definition from the previous one is that we are checking connected components between H minus F, so like the faulted sparsifier that you came up with, and G minus F rather than G, so the faulted original graph that you came up with. So it's faulted sparsifier relative to faulted original graph rather than absolute pre-faulted original. So here's an example. Here's some input graph. I'm claiming that this thing right here is indeed a one relative fault tolerant connectivity preserver. The way to check that is you could say, okay, that's the edge that might fail. If you kind of fail that edge on both sides, the connected components remain the same. This is another edge that might fail. If that edge fails, it's still fine. The connected components, there's two of them on the left side and there's two of them on the right side, and they're the same. So it still passes this check. Okay. Yeah.
I think I noticed this summer, I feel like there's something fundamental still of people's definition, that you're not forcing F to be subset of G. You're hiding behind the fact that H minus F and G minus F, which is like mathematically it makes sense, but F should be subset of G. But this definition actually doesn't ask you to put it.
That is true. What you're pointing at is a problem that shows up when you move to the data structure versions of these things. If instead of coming up with a subgraph, I just want any data structure that can report an approximate distance, then that distinction does become really important for kind of this subtle technical reason. In the subgraph version, which I'm going to focus on here, it turns out to not matter so much.
Sorry, I didn't get the objection. If it's not contained an edge of G, then it's
I guess you're right. If you are deleting, if it's not a data structure, which, I mean, if it's a data structure, the fact that you're deleting something which is part of G gives you information. You're not out, like, it already told you it's a different part of G. That's actually useful information that you can use to do something with it. So you're saying if it's a subgraph, it actually doesn't matter.
Right. From the perspective of these subgraph definitions, this doesn't matter. Like you can sort of assume without loss of generality that whatever failures occur are specifically failures from the subgraph, it turns out. But yeah, just you're absolutely right that if you wanted to come up with a data structure, it turns out to be a fundamentally different problem, whether or not you get a promise that the failing edges were real edges from the original graph.
And the problem you're solving on the subgraph is always connected components. You're not encoding any other information.
So I'm going to do the spanner version of this as we go, but besides that, yes. Cool. Okay, good with this definition so far? Okay, so the first nice thing about this definition is that it passes our first check. We want to make sure that every graph is a F fault tolerant, F relative fault tolerant for either edge faults or vertex faults.
Why?
Preserver of itself.
Why?
Why do we want this check to be the case?
Yeah, it seems to come ahead of it being fault tolerant.
So the idea is
The definition of fault tolerance in order to make this work, rather than to make it match in the way you would like a network to be.
yeah, so you would ideally like a network to be fault tolerant, but the idea is that there are some situations where you were just given a network that wasn't fault tolerant in the first place. And so you would still, like, we want our sparsifier to be as fault tolerant as possible. We want it to not be any worse at preserving connected components than the original graph was.
There are two different problems.
Right, there are two different problems. The point that I'm trying to make is that only one of these two problems allows us to prove existential results.
Did that, yeah.
I mean, that's why it's called relative, I guess. You want it to be as fault tolerant as G.
Exactly. You don't want to like lose any notion of fault tolerance by passing from G to H. You'd never want to like regret listening to the theorists. Cool. So with this definition, it passes this check since we're sort of comparing between H minus F and G minus F. It passes this check. This is only half the battle. It's not enough just to say that we have defined a type of sparsifier. It's only interesting if there are existential results that turn out to exist. So we would like it to be the case that non-trivially sparse F relative fault tolerant connectivity preservers always exist for any graph. This is again not obvious, but turns out to be true. This is a 1992 paper by Nagamochi and Ibaraki. They proved that you pay of F in the size of the connectivity preserver in order to get this. This is true for both edge faults or vertex faults, whichever version you want to think of. And it turns out this is actually, there's a matching lower bound that says that F is the correct dependence here. Okay, good. So this is like good news for this definition. There's also the spanner version of this that I want to point out quickly. So this is essentially the same thing going on. It's again relative fault tolerance. We're talking about H minus F versus G minus F. And just looking at the same graphs, I'm going to claim that this is a three spanner right here. It's a one fault tolerant three spanner. The way that you would check that is you would say, okay, for example, if that is an edge fault that we think of, then you could compare the distances between any two nodes. For example, that pair ST, but really you'd have to compare between all pairs. And you'll see that on the left, the distance between S and T is 1. On the right, the distance between S and T is 3, and that's the true post-fault, since you can go south here. And so that checks. We still have our 3 approximation. Just to cover this other little disconnecting case, we consider the distance to be infinity if the fault disconnects the graph, and that's sort of an easy case. Infinity is considered to be a 3 within a factor of 3 of infinity here. Okay, so this is good. This is a strictly stronger object that we're speaking of here than fault-tolerant connectivity preserver, since we need distance approximation to hold even after failures. So passes this first definition. I'm going to start kind of glossing through this, since basically everything from now on is going to pass this first definition. But again, we need to make sure that relative K-spanners always exist. It's getting a little bit cut off. It was set up in a paper by Lopopoulos, Narasimhan, and Smid. This was a stock paper from 1998. And they asked as an open question whether or not this is the case, whether or not they showed that this is true for Euclidean graphs, but they asked whether or not you can get non-trivial sparsity results for general graphs as well. This turned out to be a major open question in the area for about 10 years. And then finally it got resolved in this stock 2009 paper by Chechik, Langberg, Peleg, and Roditi. They showed that you get some sort of nice bound for if you want an F fault tolerant 2k minus 1 spanner, they showed you can pay a factor of F. And if you want the vertex version, you can pay a factor of exponential in F. This for sure counts as a solution for the edge fault case. It's a little bit debatable whether or not it counts as a solution for the vertex fault case, whether or not we should be happy with an exp of F. But there is at least this nice thing, this end of the 1 plus 1 over k bound right here, just as a reminder, that is the bound that was true for the non-faulty version. So we're getting this form that feels like we have some kind of nice extension of the non-faulty version. It's the necessary base cost plus some function of F that you have to pay in exchange for fault tolerance. Okay.
Sorry, question about that.
Yes.
You know, the bottom term, DFT, like it can easily go above n squared. Like what happened with that point? Can you just
Right.
skip?
At that point, you can just say it's n squared. You can always keep the entire original graph.
Sure. Good. Sorry.
Anything change whatsoever if you allow longer paths for shorter? If you allow plus a factor, plus an additive factor, so obviously you're going to do things change.
Yeah, that's a good question. The answer is yes, things change significantly. It winds up basically being a completely different problem. One nuance of this multiplicative error that I'm kind of skipping over is that it suffices to only get the approximation over each individual edge. If I can show that every edge is sort of has a nice, reasonably short path, then that can chain them together to get all pairs. Once you start introducing an additive factor as well, that's no longer the case. Now you truly have to be like considering long range pairs as a constraint. That turns out to just completely change the problem. Yes. No, it's not. I'm going to show you a progression of result that exists in just a second.
Just a quick question about the connectivity version. See, the bound you get over there is F.
Right.
So it's just K connectivity.
Yes. So for F
Yeah.
connectivity, it would be F times N. Yes, exactly. And that one is tight. Okay. So anyways, this is the result that I just showed you. This is the bound that you have to pay, like base cost of n to the 1 plus 1 over k that's unavoidable, but this red additional cost of fault tolerance factor. Fortunately, not too long after this first paper, Mike Dinitz and Roby Krupgammer came up with this different approach to the vertex fault setting that really properly closed the problem. At least, no, I'm not gonna, this isn't a type bound, I don't mean that. But like now it's philosophically unobjectionable that we're speaking about something real here. They came up with like a good polynomial in F cost of fault tolerance in this model. After that, so something kind of strange happened, which is this. So you might look at this chart and ask a very reasonable question, which is like, okay, fine, the bounds got improved a little bit, but why did we have to say this 5 different times over the course of 5 different papers? But it turns out, I'll answer that question in a moment. But basically, we know the red bound now for vertex fault tolerance, the proper cost of fault tolerance is after the 1 minus 1 over k. There's a matching upper and lower bound for this. For the edge fault setting, it turns out that things are a little bit more confusing. There's this like very strange even versus odd difference going on, but the bound is roughly square root F. And there's a little bit of an open question there that I'll mention later about what the exact red bound is. But lots of work kind of tuning the cost of fault tolerance in these models is the punchline. Okay, so the bounds for these relative fault tolerant spanners and preservers are mostly well understood. The takeaway so far, you don't really need to worry too much about the specific bounds that I was showing you on the previous slide. But the takeaway is that we can claim that these are generalizations of the non-faulty setting because we're paying polynomial F times cost of non-faulty version. And the techniques also turn out to be a nice, pleasant generalization of the non-faulty setting. I'm going to say a little bit about that. I'm going to go into techniques for a bit and then pull back out to a higher level after that. So for background, there's something called the greedy spanner. So this is the classic canonical algorithm that is used to compute spanners in the non-faulty setting. And what it is it's the natural generalization of Kruskal's algorithm, if you remember that. Kruskal's algorithm being the most common way to build spanning trees, in fact, minimum weight spanning trees, if you like. All you can do in that algorithm is you just consider the edges one by one and do a greedy thing. You say, if the current state of my sparsifier suggests that this edge is necessary to add, then add it. Otherwise, throw it away. This is doing the analogous thing for spanners, saying just consider the edges The order doesn't matter because we're in the unweighted setting, but in general, you have to consider that an increasing weight order, just like the algorithm. And you say, check whether or not we currently have the distance between the endpoints of this edge is currently too much. And if so, add a picture of how that's going to work. If we're trying to build a 3-spanner, it's initially empty. We would consider the edges one by one. So first consider this edge. Distance here is 1, distance here is infinity. So we would choose to add that edge to the spanner. Then consider this, same calculation would make us add it. Consider this, add. Then we would consider this edge right here. The distance here is 1, the distance here is 3 in the current spanner. That's good enough, so it's safe to throw that edge away. And that's the final spanner that we would get from this greedy algorithm. Okay, so this is popular because it is very simple to prove correct. It's like almost instant that it produces a valid spanner. There's also this nice structural property that will help with the analysis. There's this prominent 4 cycle in the input graph. And that 4 cycle did not survive in the spanner. And it didn't survive because it's a 4 cycle. It was the other edges of the cycle that betrayed this last edge in the cycle and caused it to get thrown away. And it's always going to work that way. And that is key to the analysis. So this theorem that was proved in this 1993 paper that I mentioned earlier, that gives us our non-faulty bound for spanners. What it does is just 2 lemmas long. The first one is this observation I just made. It says that the output spanner has high girth. It has no short cycles. So girth is the shortest cycle length. Since we have k equals 2 here for a 2k minus 1 spanner, we're claiming that it will have no 3 or 4 cycles for the reason that we just said. So that's always the case. And then you get to apply this very classical bound from extremal graph theory. This goes back to like the 40s, called the Moore bounds. This just says that any endnode graph at all, whether or not it came from this algorithm, if it has high girth, it can only have this many edges in it. This, by the way, I think this theorem is very funny. It's called the Moore bounds. And Moore is the name of a famous graph theorist who was working in the 1940s. And yet it's considered folklore for some reason. It's sort of like if there was something called Bodwin's theorem, and you were like, okay, who proved that? And I was like, I have no idea. It could be anyone. But that's, I don't know. I don't make the rules. Honestly, I think Moore's career is going to be fine without these citations. So yeah, that's what we got. Anyways, so given that that algorithm is like nice, simple, easy to prove correct, it's like the textbook algorithm for non-faulty spanners. The natural thing to try in the faulty setting would just be the analogous greedy algorithm. So here's what it is. It's the same algorithm as we did before, but that blue part is new. So instead of just checking the distance between the endpoints in the spanner, we're saying if there exists any fault set at all where those failures would make the distance too large, that's the case where we need to add the edge. Otherwise, throw it away. So to give just a quick sort of rundown of how this would work, going through the same example with a slightly different graph, we would add these first few edges for the same reason as before. Sorry, I think my clicker's dying. So we would add these first few edges for the same reason as before. We would get to this edge. This is one that we previously added. But instead of adding it, we would say, or sorry, we previously didn't add this. We threw this edge away. But instead of that, we would now have to say, well, what if that edge faults, or that node faults right there? That would be a problem. If that fails, then the distance between you and B is infinity. So therefore, we actually need to add it this time. However, once we consider that last edge, you can kind of check that the distance between these 2 nodes in this current spanner that we're building is going to be 2, regardless of what node fails. And so therefore, that edge remains safe to throw away in the 1 fault setting. Okay, so this seems like the natural thing to try, right? So it is the very natural thing to try. For technical reasons, it was hard to analyze and was not actually touched for about 10 years since this literature. But eventually this got approached. The way to think of this is that since this non-faulty version of the greedy algorithm made graphs with high girth, and that was really important, you should intuitively feel like this is some similar algorithm, and therefore it's going to make us graphs that are structurally close to high girth. Not clear what that means. And when I say close to high girth, I don't mean that like it has girth 2k minus 1 instead of 2k or something like that. I just mean there should be some kind of structural similarity between these graphs and the high girth graphs. So this makes sense, but the question is how to formalize. And then this is a thing that I did in a paper with Shumwell Patel. He's a student at Columbia now. This is when he was an undergrad and I was at Georgia Tech. We kind of figured out the way to formalize the sense in which these graphs are close to high-growth graphs. And the concept there is a blocking set. I'm going to call it a vertex blocking set here. And it has this kind of technical looking definition. It's like a pair of vertex, comma, edge. It's a set of vertex, comma, edge pairs with the property that all short cycles get hit by one of those pairs, by both the vertex and the edge. The intuition you should have is that if I were to tell you that a graph has a k blocking set of size 0, that is equivalent to saying that it has girth larger than k. It has no short cycles that need to get hit at all. And so therefore, if I tell you that some graph has a small k blocking set, you should think of that intuitively as expressing that it's structurally close to some high girth graph. Okay, when we say something about where this definition comes from, it looks a little bit technical and strange until you inspect that greedy algorithm that I just showed you a moment ago. So in that greedy algorithm, when we're like looking at some edge in the input graph and deciding whether or not we want to add that to the spanner, we choose to add it to the spanner only if there exists some vertex fault f that hits every single short cycle that got closed by that edge. So this edge does close a 4 cycle, but that 4 cycle got hit by that vertex fault. That's kind of the point. So the reason why this works is every time this greedy algorithm adds some new edge, every new cycle that gets added to your graph must get hit by a pair that's like that vertex fault, comma the edge. Both of those need to lie on this new cycle. And therefore, we're always going to get a blocking set coming from that previous algorithm that only needs to add at most f pairs per edge.
Then the conditions tailored to one vertex removal or any f removal?
This works for any f. The claim here is like, because this particular picture is for f equals 1, we only need to speak about one block. But even if we were talking about more faults than just one, if there's like f1, f2, f3 failing vertices, then we would just include each of those 3 failing vertices paired with the new edge as a block. Okay, I think this is the most technical slide in the talk, so I'll pause for questions, but we're gonna like stop doing proofy things after this.
Say if I run the 3D algorithm, it keeps me blocking set of certain size. Or
Yes, I did. So specifically, let me put that lemma up. The thing that we get from this is that upper bound that I was claiming before, that the price of fault tolerance is after the 1 minus 1 over k. And the argument uses these 2 lemmas right here, which are just analogs of what we were doing in the non-faulty setting. So the first lemma that we used before said that the output greedy spanner had high girth. Now the claim is just that it has a small blocking set, which you can think of as being like close to having high girth. Specifically, you get this down next time the number of edges in the spanner. And then there's this like blocking set more bound. So it's some sort of extension of the previous more bound argument that just said if you have a small blocking set, then your graph must have most of this size. I'm not going to show you the proof of this, but it turns out it's very short. It's only like half a page or something like that. The argument is basically you just say, take your graph, consider a random subgraph of it. The blocking set probably won't survive that random subgraph, and so therefore it's high. And if a random subgraph has high girth, that tells you something about the sparsity of the original. It turns out that it's better to do a random induced subgraph and keep vertices with some probability, but that's just sort of, morally speaking, yes, it just turns out that's a technical optimization.
But the sampling rate is what?
The sampling rate is about 1 over f for the vertices. This will almost kill the blocking set, and then you can kind of just like remove a handful of edges after that to completely kill it. So the bound on the blocking set is a factor of f times the number of edges that you ultimately choose to add to your spanner. This
won't be at least 10.
so this bound, so typically, yes, you'll typically add at least 10 edges to your spanner. that you're constructing, so that would give you at least n of this blocking set. Cool. So take away from this slide, like what you should know going forward is just that, like, in addition to these actual bounds being generalizations of the non-faulty setting, so too are the techniques. All you got to do is hit it with the simple greedy algorithm, which is like clearly producing a correct sparsifier, and then you can kind of do some reasonable extension of the lemmas that are used in the proof. I'll say one more. Actually, sorry. There's one sort of catch going on with this algorithm. I'm curious if anyone has any ideas. It's completely correct, but there's a reason why this is sort of an undesirable algorithm. Yes, that's exactly it. So that piece in blue right there currently exists a set of small vertices that makes the distance large. The naive thing to do is just like brute force that. You could try all possible failure sets and check the distance each time. That'll be runtime n to the order f, which is not great. We want f to be maybe a small polynomial. So that's not desirable. It's time to brute force. You might then ask, okay, fine, but can we do better than brute force? When people first see this, they're often like, well, yes, this is min cut max flow, but it's not. It's not min cut max flow. This is a trap. So it turns out the question of whether or not there exists this small set of nodes that cuts all paths of short length less than or equal to k. In the case k equals infinity, this is min cut. You can use min cut max flow, and it's very doable. So as a result, this algorithm does work just fine for connectivity prisoners. But for spanners, this is called length-bounded cut when you have this k parameter. This is an NPR problem. This was proved in a 2006 paper. So this algorithm that we're pointing at right here just sort of inherently runs in exponential time. And that algorithm itself is unavoidable. You're not going to speed up that if condition that's making things run slow. But that's why we needed like 5 papers to say this over and over again. The first of these was by Mike Dennitz and Caleb Rebel. They basically showed that if instead of brute forcing this NP-hard problem, you just run an approximation algorithm for length-bounded cut, you'll basically pay the approximation factor of spanner size. So they were able to get only an additional k factor of spanner size in exchange for a polynomial time algorithm, which is pretty good. Then me and those two same authors did something more complicated that also was polynomial time and removed that k factor. And then a couple of stocks ago, Ralph Carter came up with some totally different non-greedy algorithm that runs in near linear time. I think this is shocking that such a thing should exist. I would have bet any amount of money that you needed to at least pay dependence on f in order to get f fault tolerance. Turns out that's not true. Turns out you can have f fault tolerance in near linear time for any f. Cool. So these are the papers that were sort of showing up over and over again. There's one more. There was this business about edge fault tolerance, which I'll gesture at here. So you could sort of do this edge fault tolerance spanner greedy algorithm. This is essentially the same thing as we did before. We're just talking about failing edges instead of failing vertices. Besides that, it's the same. So like when you look at this edge, you would still choose to add it, but you would choose to add it because of that edge fault rather than because of that vertex fault. But essentially the same algorithm. With this algorithm in mind, the natural thing to try would be an edge blocking set, which is to say that instead of considering edge vertex pairs that hit your cycles, you're now going to consider edge pairs that hit your cycles. This is for sure the right first attempt. It is easy to prove the natural analog of that first lemma, that the greedy spanner will result in small edge blocking sets, so things that are close to Heidgerth in that sense. However, it turns out that this does not imply any meaningful sparsity. So something goes slightly wrong, even though it feels like you should try this. It turns out to not be the right definition. This last paper that was on that previous chart basically turns this into what we're calling strong edge blocking sets. Strong edge blocking sets are acknowledging that these edges arrived to the spanner in some particular order. And it's not just that there's an edge pair that hits your cycle. Also know that one of those two edges was the last edge to have arrived in the cycle. Strong edge blocking sets are just encoding this extra little detail of graph ordering. And it turns out that that significantly strengthens things. Once you use this notion of blocking sets, you suddenly get a much better price of fault tolerance upper bound. Okay, I'm not really going to say why that's true. More what I'm trying to do with this slide is gesture at the idea that like once we move from vertices to edges, suddenly our definition of blocking sets got a little bit more complicated. We started having to talk about edge ordering. There's a bunch more work that has happened that invokes this idea of blocking sets, especially for related problems like emulators and light spanners, if you're familiar with those. If not, it doesn't matter. But the only piece of this that truly grows in complexity is the definition of blocking sets. These get crazy, honestly. There's like one paper that uses something called salad blocking sets, where this is like a 5-term acronym for all of the properties that it needs to have. So the game that you wind up playing when you do these papers is like, come up with some like very precise cocktail of properties for your blocking set that's going to enable this greedy algorithm analysis to work. Good. This last little open question that I'm going to leave you with in this relative fault tolerant setting. This is for even k that is 4 or larger. That is the only setting where we do not know the correct price of fault tolerance. Specifically in the edge setting, we know that it's somewhere between those two numbers, but there's a polynomial gap. This is like a very interesting question from the perspective of like cycle combinatorics and graphs. It turns out it gets at some fairly deep stuff that way. But honestly, this does not have much to do with the philosophy of fault tolerance. Like whatever the right answer winds up being, it's not going to like reveal anything too serious about what the right definition of fault tolerance is. Okay.
So the algorithmic problem there, like deciding if the most edges, which I mean, that's still hard, but the same solutions work.
Yes, exactly. So it's just a slightly different version of like boundary cut that's still NP hard, but the same fix it. With the exception that Murav-Carter's algorithm does not still work in the edge setting. That's specific to vertices.
Could you sort of sketch that out and the part and then
Yes, it is a hierarchical clustering algorithm. So the basic idea is you'll like sample level 1 centers in your graph with some probability, sample level 2 centers with some probability, sample level 3 with some probability. And then your goal is basically to make sure that every node can reach all of its nearby centers using F node disjoint paths. So you essentially have the option of like, if you are too far, this node is too far away from the node that it's trying to get to, it has some like very well protected way to just sort of go up a level in this hierarchical clustering structure. And then the top level centers are just given these extremely good paths to all the other nodes in your graph. Yeah, sorry, that's a bit sketchy, but hierarchical clustering is kind of the magic that's going on in it.
Is that algorithm, Murav, like analogous to any non-fault tolerant algorithm?
Yes, there's a Botswana-Sen have an algorithm for non-faulty spanners that also uses this hierarchical clustering. Murav's algorithm is sort of this, it's an extension of that, but that undersells it a little bit. She had to do like a lot of technical work to make it work with faults. Cool. Other questions on relative fault tolerance stuff? Because I'm about to tell you why it's bad. Why we shouldn't have been talking about this.
I guess I'm a bit confused because I thought you said like at least for fault tolerant connectivity preservers, F times N was optimal. But here you're telling me you can get root F at the cost? Like
yeah.
more general or
That's a good question. I was sort of lying to you to simplify things. It's actually root F plus Fn.
Okay.
So there's just, you can never beat Fn, but like in the parameter regime where root F is less than that, you get this.
Okay.
Yeah, thanks. Okay. Cool. Good with all this? Okay, so now let me tell you a critique of the model that we just talked about. So in practice, when things fail, there's sort of two different situations you can imagine. It's typically the case that faraway failures occurring in different parts of the graph are either independent from each other or they are correlated with each other, but it's almost never the case that they are anti-correlated with each other. So to give you a metaphor of what I mean here, let's imagine that there's a bunch of traffic jams going on in Waterloo right now. Given that fact, what do you think is happening in Ann Arbor right now? Should you expect more or less or the same number of traffic jams as usual? This is kind of a metaphor for fault tolerance. So I'm going to claim it's a little bit unclear. Like there might be local reasons why there are traffic jams happening here in Waterloo. For example, there's a bunch of construction or something like that. If that's the case, you would sort of expect this to have no effect on Ann Arbor traffic jams. There would just be the usual number, at least according, they would follow the usual distribution, whatever that is. It also may be the case that there's some like more global reason why there are traffic jams in Waterloo. Maybe it's like Christmas and everyone is traveling and that's what's causing the traffic jams. If that's the case, you would expect there to be more than the usual number of traffic jams in Ann Arbor. But there's not really a reasonable case where knowing that there are traffic jams in Waterloo cause you to believe that Ann Arbor traffic is unusually good, that it's more clear than normal. They should not be anti-correlated in that way. Similarly, if a communication link fails in some network, that's sort of the original metaphor that we had, should you expect random, like if this is just sort of some random failure, it's not really going to have an effect on other parts of the network. Could also be a systemic failure, some sort of architecture is breaking in some serious way, and then you would expect more than the usual number of failures elsewhere. But the point is that you're not going to have anti-correlated failures. And
the case in networks too. I mean, if everybody's watching Netflix, like somewhere else is going out lower traffic, it's going out lower fonts.
yes, so I'm sort of hiding some stuff in this far away claim. So like it's some sort of locality network of like if you put Netflix next to, I don't know, some other streaming service, then like maybe they have some sort of influence on each other. But like in communication networks, it doesn't tend to be that way. Like only nearby things could very reasonably have some influence on each other, but far away things will not so much.
Do networking people study these things, for instance?
So
Like do networking people also study these things, and because this assumption comes from networking, or is this more of a theory?
this is more of a theory assumption. It's like, so the maximum number.
No, the fact that they are like anti-correlated, is it more like a theory thing that is nicer to work with, or this is actually what, like actually people like build systems observe this?
So this is coming from systems and networking. The point that I want to make though is that the model that I was using a moment ago, this relative fault tolerance model, this is actually an anti-correlation model. And so this is more like an objection that systems people have to the relative fault tolerance model. That's what I'm pointing at. Let me say a little bit more about that. So here's Ann Arbor. There's 3 roads I've decided leaving Ann Arbor. And if there's 3 roads leaving Waterloo, if I were to tell you that there are F faults happening that are adjacent to Waterloo, these 3 roads are failing, in the relative fault tolerant model, that forces there to be 0 faults touching Ann Arbor because you've spent all of your faults in one part of the graph. So this is precisely the type of anti-correlation that we're saying does not model reality very well. Okay, so this is the objection to the fault tolerant model. And there was this really interesting thing that happened, which is I was on a project that sort of like took this view of things. We were like, maybe this is not such a great model for this reason. Meanwhile, concurrently, another lab in Weizmann also had the exact same thought. They were like, they were sort of pointing at this anti-correlation being an undesirable feature of the relative fault tolerant model. And we came up with 2 completely different solutions to this that point in exactly opposite directions, but are both true. So let me explain those next. So one of the models, I'm going to call this 3A. I'm going to call this the degree fault tolerant model. So what this is, it's the same like relative thing going on as before. We're comparing H minus F to G minus F. But the difference is that previously we were saying your failure set can be any F edges. Now we're saying your failure set can be any set of edges at all, as long as the maximum degree of that edge set is. So this is a vastly larger set of potential failures. Up to n times F edges could fail in your graph. The only requirement is that they're kind of spread around the graph in some way. They didn't wind up being too concentrated in one place or another. So this is strictly stronger than the model we were talking about before, which in some sense makes it a more desirable model, except that we got to kind of pass these checks before we're sure that it's a reasonable definition to work with. So, yeah.
We're talking about node failures at one stage before, not edge failures.
Yeah, so all of these definitions can apply to both edge failures and node failures. I'm going to draw this one with edge failures because I think the picture is just a little bit more intuitive, but there's also a node failure version of this that makes sense as well. So here's your input graph. We're talking about a 1 edge. So this graph right here is a 1 edge fault tolerant connectivity certificate. However, it would not be a 1 degree fault tolerant connectivity certificate. The reason is that this particular set of edge failures, this is a degree 1 set of edge failures. And node is only touching 1 failing edge. And yet, so it's not a degree fault tolerant connectivity certificate. So we are speaking about a stronger object. But to give you a positive example, if that's your input graph, modifying it a little bit, this is indeed a 1 degree fault tolerant connectivity certificate, even though we removed that edge crossing the middle. If you look at any degree 1 failure set, things will have the same connected components on both sides. Okay. So is this a good definition? So yes, it passes the first check that everything is a reasonable sparsifier of itself. The question is then, does this second condition get passed? Do non-trivially sparse sparsifiers exist under this degree fault model? That's the real question here. And given everything that I just said, I'm actually going to strengthen this a little bit. It also now kind of seems desirable that some sort of greedy algorithm and an analog of the previous analysis ought to work if we're talking about something that's a reasonable extension of what we were doing before. This is definitely not obvious, but this turns out to be true. So this was a couple of Soda papers. Ralph Partner was on both of them. It was me and Bernard Huppler on the first one. So it turns out that we got some sort of reasonable bound for F degree fault tolerant connectivity preservers and F degree fault tolerant spanners. And you get all of these just by running exactly the same greedy algorithm, but with respect to this. All of the other stuff applies as well. You can make things polynomial time using these tricks from these other papers. So it turns out that this does exist. The takeaway from this is that we can work in a much, much stronger fault model. We can tolerate many more fault sets than we did before. And we still only have to pay this like very reasonable cost with whatever the base spanner cost is or base preserver cost is times the reasonable polynomial in F. And the only real like assumption that we have to make is this. We have to say that the faults that are occurring, even though there's more of them, they kind of have to be uncorrelated in some sense. And what I mean by uncorrelated is that if you imagine a random fault set occurring, it will have this property of being spread around the graph in the way that I'm talking about. For example, as a corollary of this, you can pull out the fact, sorry, it's kind of getting cut off. This just says that if you literally were to work in the random fault set model, you need to tolerate a uniform random fault set with some probability. You can achieve the same size bound as before, as long as these are independent failures that are occurring. So this, I think, is a good model of independence. It's sort of saying like, okay, independent failures is the good case. You want to tolerate more failures, just pray that they're independent. That's how you do it. Then this model will help you. Okay.
Like this key thing that is there a for set that can be done? Or?
Yes, so that step can be done, but it becomes more complicated and you have to lose like more, you have to lose like several K factors in order to do it or something like that. So there's a bit of a cost and it's a bit more complicated, but overall the method works, gives us something.
K is so you lose K in this side?
Right, so you'll pay a K factor in the size, which is not too bad, it's at most log n. Okay, so this is model 3A, that like you can tolerate more faults so long as they're independent. Meanwhile, this lab at Weizmann, Petrushka, Shapir, and Salik, their names are getting cut off up there, but this is an ITCS paper. They came up with this definition of color fault tolerance to address exactly the same objection. So this definition of color fault tolerance is, we now imagine that the input graph has edge colors. This can be literally any edge colors. It's not like a proper edge coloring or anything like that. You could even give all of the edges the same color or all of the edges a different color. That's all allowed in this model. And what is happening with the failures is that the rule is that F color classes can fail. But everything in one color class either fails or doesn't fail. Those are the rules. So for example, if that's your input graph with whatever colors I do, this is a correct one color fault tolerant connectivity certificate. The way that you would check that is you would say, okay, maybe the blue edges fail. That's one possible failure event. If you fail the blue edges on the left and you fail the blue edges on the right, you'll see that they're the same components on the side. It's an isolated vertex and everything else is together. Another failure event, for example, that could happen is that the green edges fail. If you fail those on both sides, you once again have the same connected components in both ways.
So in this definition, do I have at the answer has to delete all the blue edges or some source of the
all the blue edges. So you choose up to F color classes, and those color classes fail entirely. Every single blue edge either fails or doesn't fail in particular failure events.
And the color was still to you.
And sorry?
The coloring.
Yes, the coloring is part of the input. So you're given this input graph with edge colors already attached to it.
Doesn't this model restrict the adversary too much? Because now their options is very limited because you have to delete the entire color class, which destroys G minus F, like makes G minus F very loosely connected as well.
So G minus F could be very loosely connected as well. Let me point out that what we are speaking of here is a strict strengthening of the relative fault tolerant model for the reason that if the same edge colors is the same. And now this is sort of saying, okay, you could potentially handle many more than just F failures. However, the thing that is going to let you handle much more than F failures, potentially like n times F, or some very large number of failures here. The thing that really lets you do that, so these exist. I'm going to sort of skip over that because I think we expect that at this point. But the thing that lets you do that, the takeaway is that you can have this much stronger fault model that can tolerate more things and handle way more than F failures. And you still only have to pay like the right cost form, base cost times a polynomial. But you can do this if the failures are extremely correlated with each other. It's like all of the blue edges either all fail together or all don't fail together. So this is really confusing. These papers, despite both addressing the same thing, reached exactly the opposite conclusion, which is that uncorrelated failures are the good case, or correlated failures are the good case. And now nobody is sure what's going on, is the short answer. So to sort of say what the next steps are, I'm almost at time, so I'm just gonna sort of conclude here. We started with this relative fault tolerant model that said there were a maximum F failures that could occur in your graph. The degree fault tolerant model is a strict strengthening of it that intuitively is capturing this setting of independent or uncorrelated failures. The color fault tolerant is also a strict strengthening of the model that captures correlated failures. And the real open question in the area right now that I think is by far the most important one, more so than tightening any of these big O bounds that I've been mentioning, is just what is the one true definition of fault tolerance? So there should be some kind of model that is a common mutual strengthening of these two that somehow both captures the correlated failures and the uncorrelated failures, presumably some stuff in between. But I don't really know what it is, and I don't think anyone knows what it is. This is what's being discussed in the community, and there's a bunch of different kind of definitions being thrown around and people arguing philosophically about this right now. So I'll point out one thing that kind of works, but in my opinion is not really right. You could just sort of take the natural join of those two previous definitions, and you get this. You get degree color fault tolerant, where it's any set of colors can crash as long as every node is touching it in most F failing colors. This would be a natural mutual strengthening of those two models. It is an open question whether or not this is a reasonable definition from the perspective of a good existential result existing. And this might be the right next step for the area, just to figure out if we could even unify these two different directions to this extent. But to be honest, the better open question, this feels kind of lazy to me somehow. It's just taking the join of two previous definitions, and it's not that philosophically motivated in the same way that all these other definitions were. I have higher hopes than this. I think there's going to be one true definition of fault tolerant spanners out there. So to sort of just give you my final wrap-up slide here, the story has been that for many years, about 10 years or arguably more, the prevailing wisdom was that you should care, if you want to evaluate the price of fault tolerance, you should just ask yourself what's the maximum number of edges that could possibly fail. This is how everyone thought for a long time. And over this last year-ish, the wisdom has shifted to we are in search of some other much fancier statistic of a fault model that is going to wind up being the more natural cost parameter in terms of evaluating the price of fault tolerance, but we have no idea what that is yet. So there are at least 3 papers that are coming out in 2025 that are specifically about the degree fault model. There are at least 2 papers coming out in 2025 that are specifically about the color fault model. And this is just, they're sort of the area is just running with both of these directions, and the next really good paper I think is going to be whatever finally unifies them and gets all of this going together. Okay, but the takeaway from this entire talk is that the conceptual open question that we should care about in this area is what is the one true definition of fault tolerance? everything that I've said so far is a clue as to that definition, but I don't think any of them are the one true definition. So the talk was titled The Quest for the One True Definition of Fault Tolerant Spanners. The answer is I don't know. I don't have a satisfying answer for you, but maybe the one true definition of fault tolerant spanners was the friends that we made along the way. So thank you. That's all I have.